Today I want to talk about the FLRW metric, which is the Friedman Normality Robertson Workers metric, which is the basics of the cosmology. In the large-scale structures, the observable universe is almost homogeneous and isotropic. It's not depends on some translation transformations through the simulation. Now we can construct such homogeneous isotropic matrix with this several terms. There are some curvatures and scaling factor. First of all, we can parameterize as a four-dimensional sphere, like as x1 squares plus x2 squares, and so on, x4 squares equal to the r square. And the surface of such a four-dimensional sphere is actually three-dimensional. The degrees of freedom is three. And we can parameterize of such a spheres in terms of the sines and cosine. Is the same with the circles of the three-dimensional sphere. And we can write that the space interval, three-dimensional space intervals like this spheres are given like that, and in terms of the also angle of the size and solid angles large omega. Similarly, also we can construct of the negatives curvatures hyperboloids in the four dimensions, and there is also three-dimensional surface, and there are minus signs for the other components, and it can also parameterize with the hyper trigonometrics. And the spice intervals of such as spice is parameterized with the hyper signs. And similarly, we can construct of the plane which has curvature 0, so that's the same as the Pythagorean's distance. And the curvature is defined as curvatures are defined as one over the squares are the radius of the spheres through the hyperboloid, and we ignore that as such scales of the curvature, size of curvature. We will just focus on the size of the curvatures, a small case. But the sphere still has a positive curvatures one, and the hyperboloid that has the negative curvatures. And therefore the plane. And we will change the variable. Instead of the chi, we will introduce the law with the sum of the radius of r. Then we can change the variables such as sine chi and the hypersine chi. Instead of the chi, it is change of the law, which is a radial directions coordinate. There is some relation between the radial direction r and the law. So we can change the d law. Metric can be expressed in terms of the dr. So we can write out the three-dimensional surface space intervals in terms of the dr and some solid angle part, and there will be some curvature terms will be appears as in the denominators of the dr. And such as the spatial parts are inserted in the metric, and there will be some time components. And important thing, there will be some of the scaling factor, which is like expressed as universe expansions, cosmological expansion. So such as FLRW matrix contains of scaling factors to express sort of the universe expansions, and there will be some of the curvature terms which express some of the curvatures of the space-time manifolds for the universe. From this FLRW matrix, we can calculate the Christopher symbol. First of all, gamma zeros one is represented sort of A and I dot. And gamma ij case for the spatial part matrix. And gamma ij also represented by the sum of the A dot over the I. And also we can calculate the Riemann curvature, and we can also induce the manipulations by the Einstein specifications, but I will discuss in the next sessions. Also, we can define some other coordinates, conformal time is as the cosmic time dt. Such conformal times defines the integrations of the times over the integral sort of the one of the i's over the time. And if we define the conformal time like that, then the such as the dt's can be changed by like that. So the atlas and the spatial components are inserted in the scaling factor. So in the this resumes just a part of the matrix is scaling factors in terms of the as a functions of the complement times and just the multiplication of the mean cost B matrix. The complement time is very used to understand the same times lost, just multiplying sort of scaling factors to mean cost B matrix. I want to mention some remark, some intention in the cosmology before the start. We will use some gravitational constants and h bars and c equals to root 1. That are some of the Planck units and some of the dimension units of the gravitational constant h balance is given like that in terms of the position, time, and the mass. And if we use the Planck unit, the gravitational constant is the one of scale, so h balance equals to 1. Then we can define the Planck mass as the combination of the h balance c and z becomes the dimension of the mass. So from that, if we insist that h balance equals to 1, then the Planck mass equals to 1 over the root c, and it has a 10 minus 90 kilograms, very extremely large. And we use that Planck mass to express the gravitational constant. Next, I want to talk about some of the scaling factor. Scaling factor is a function of time. And we can define the Hubble parameters like a does the a, and then we will denote the present Hubble parameters like zeros. And if the scaling factor is the largest and the wavelength is the largest, it makes a larger shift. So there are some cosmological large shift by the expansions. There are some of the measured volumes, and there are some initial wavelength, and we can define the roll-up shift parameters 1 plus that. And because the lambda 0 is equal to the I0 over the I0, because the lambda is a proportion to the I, so we can deduce the parameter shifts just from the scaling factors. From that, by observations of the shifts, we can determine sort of the current values to the Hubble parameters equal to the almost 7 kilometers per second, the velocities over the megaparsec case from the Hubble's law is equal to this HSR. And we will use this the parameters in instance such as some complicated units, just 100 times that are small h and the small h that are the 0.7. We will use these intentions to express the expansions. Maybe that's an assumption. We'll talk about some Brodmann equations from the FLRW matrix using the general relativity theories and also derivation of the lambda CDM model, which is standard cosmology.